Hi, this is going to be a series of lectures on functional analysis, but I'm going to start with the Hahn-Banach theorem. Probably I may do 3 videos. We'll go slow as usual. We will try to understand in depth. Okay, so let us go to the job. Yeah, this is my channel. See, I had published so far about 360 plus videos on my YouTube channel, and YouTube does not have a proper way of cataloging them. So the best thing will be to download the list of videos from here, or you can also scan this and search for the list of videos. The list will give subject wise like real analysis, group actions, or let's say complex analysis. Okay, within real analysis again, infinite series, continuity, differentiation, and then several variable calculus. Okay, and topology. All these things will be given in the order of preference, so it will be best. Okay, so I would suggest you please download this. It will be periodically updated. Okay, now I'm going to follow the book written by me and my co-author Sukumar. That's on functional analysis. It's not an introduction. It's a first course. Okay. I'm sorry for this thing. Even my own book, I didn't remember the name. It's a first course. So let me just write this. Okay. Right. The especially section 2.1. So let us get. Oh, I have not screen shared. Yeah, it's shared. Okay, great. Okay. So what does Hahn-Banach theorem says? Let X be a non-linear space. I will write NLS, which is non-linear space. Yes. Right. Suppose Y. This is my notation for a subspace. Okay, vector subspace. Okay, not necessarily closed. Okay, no topological assumption. Okay, just a vector subspace. Right. And suppose I have, and let's assume this over a space R to start with, or later also over C. Okay, and I have a linear functional to R. This is a continuous linear functional. So what does that mean? I am using this after about 2 months, so I just have to get used to this again. Okay, what does that mean? There exists some constant C, so that for all y in y, mod fy is less than or equal to C times norm y. Okay, then we say, okay, this is uniformly continuous actually, right? Okay, what does the theorem says? If the theorem says, Hahn-Banach theorem says there exists a function g from x to r such that g is continuous, linear functional, and g restricted to y is f. That is for all y in y, g of y equal to f of y. So that's what g is we call g as an extension of f. We call this as an extension. An extension, it may not be unique. Okay, this kind of problems are very common in topology. You must have seen in Tietz extension theorem in a completely regular space. If you have closed subset and a continuous real valued function, you can extend it to the full space and keeping the supremum the same. Okay, so these are all the very common problems in analysis. Okay, now this is the theorem we want to prove, and many times the students have a lot of difficulty in understanding. I hope the result is clear, right? So let us look at this. This is my x and this may be my y. I just pass through origin. Okay, this may be my y, and from here to this I have f. Then what do I want? From here to here I want a g to r, but then when I restrict to this, okay, g of y turns out to be f of y for every y in y. And this must be continuous, this must be also be continuous. Yeah. Okay, pause. Understand this statement. Let me just make sure I started recording. Yeah, right. Okay. And also recall what is states extension theorem. So these are the extension theorem. Hahn-Banach theorem also an extension theorem. Right? So my plan is to look at it the simplest case. The first thing is purely algebra. Okay, suppose X is a vector space over a field, Y is a vector subspace. I have a linear functional. Okay, there is no topology now, right? And over any field also. Okay, there is a linear functional f from Y to the ground field f. Then can I extend it? Okay, this is the problem. So let me just, okay, we will first look at the algebraic version. So I have a field capital F. This is a field, and okay, my V is a vector space over the field F, and W is a F vector subspace. Vector subspace. And suppose F from W to F is a linear function. Notice that, as I said, F is any field, okay, therefore no topology, and therefore vector space, this is no topology, it's purely algebra. Therefore, what is the question I want to ask? The question is whether there exists a G from V to F, which is a linear functional, so that when I restrict G to W, I get F. That is for all W in W, G of W equal to F of W. Does there exist? Okay. Surprisingly, the answer to this is extremely simple. Just one line answer if you want. Okay. So what do we do? Let us look at BW. Choose a basis. Okay. Some basis, a basis of W. Okay. Choose a basis. Right. Now this is a linearly independent subset. Set of B. Right. So there exists a basis B of V such that BW is contained in B. This is proved by Zorn's lemma. Why I use Zorn's lemma? Notice that I said it's a vector space, it need not be finite dimensional. Okay, could possibly infinite dimensional. And similarly W could be anything. You understand? Right? In fact, the typical proof existence of basis, okay, uses Zorn's lemma. What it says is if V is a vector space over a field F, and if A is a linearly independent subset of V, then there exists a basis B of V such that A is a subset of B. This is the version you usually prove. This is a theorem. When you proved the existence of a basis, this is the version you would have proved. Okay, any linear independent set can be extended to a basis. Usually in usual first course in linear algebra or finite dimensional vector space, you would have seen this without any appeal to Zorn's lemma. But in the case of infinite dimensional, you will apply Zorn's lemma. Right? Okay, accept all these things. See, even if you are not learned that thoroughly, just accept it. Okay, this is the way you have to kind of put everything in place so that you can see the complete picture. Okay, let's come back. Right, now let us look at F. Right, now I will define G from B to F by the following: G of W equal to F of W if W is in B and actually W is in BW. BW is contained in B, right? Right, and G of X equal to 0 if X is not in X is in, okay, let us say X is in B but not in BW. right? Now I have defined G on a basis to F, therefore extend this linearly. To all of B. Okay, let us recall what does it mean. If you give me a vector B in B, then I know there exists, okay, B1 to Vn in B and scalar C1 to Cn in F, so that my V is C1 B1 plus Cn Bn, right? Therefore, how do I define G of B? G of B I define to be C1 G of B1 plus Cn G of Bn, right? Okay. Now notice that if my V happens to be in W, then my all my V1 will be to Vn must be in BW, right? Therefore, in that case, G of B becomes G of G1 B1. But remember, G, this is F of B1 plus Cn F of Bn, right? Remember, how did you do? G of W equal to F of W if W happens to be in BW, right? Now my V, since V is a vector in W, therefore, and remember with respect to the base, it's a linear combination. But since V is in W and BW is a basis for this, then V will be something like D1 W1 plus DM WM, okay, where W1 to WMN are in BW, right? And DJs are scalars, right? But this is also equal to C1 V1 plus Cn Vn, where V1 V2 Vn are in basis, right? But remember, W1 to BW is contained in B, therefore W1 to Wm they are also in B. Since this is a basis, this is a unique linear combination that shows that M must be N, and but for permutation etc., okay, W, some W must be say some corresponding B. Okay, this is a pure algebra. Please learn that. If you are slightly not so sure, because linear algebra you just learn how to work with things, please understand. Okay, uniqueness of the expression implies M must be N and some V I must be some Wj. Okay, for each I there exists a J of I. Okay, and therefore this is the same. Are you following? So what is the conclusion? Therefore my V1 V2 Vn have to be in W, and therefore G of V1 will be F of V1 etc. Okay, therefore my G, okay, restricted to W is nothing other than F of W. Okay, so pause, review, proceed. So the algebraic version, the extension algebraic version of Hahn-Banach theorem is easy. If your linear algebra is good, it's utterly trivial. But what I want to do in the rest of the lecture is to give a complicated proof. You saw that here we use the existence of extension of linear independence, namely a basis of BW to a basis of V, and from that we got this result, right? But to do that, I already said, indicated in the original algebra book, you will see that Zorn's lemma is used, right? Now what I am going to do is I am going to directly use Zorn's lemma to get the extension without appeal to any linear independent set can be extended to a basis. Okay, I am not going to appeal to that. I am going to use directly Zorn's lemma, because if you learn this, you will see the analytic version which you are going to do in the functional analysis part will become actually easy for you to understand. Okay, that's the reason why I start with the simplest case. So let us go slow. Let us look at what is Zorn's lemma. Okay, suppose X is a partially ordered set. Okay, what does it mean? It's a partially ordered set given any X, okay, x1 x2, okay, right? I may not be able to say x1 is less than or equal to x2 or x2 is less than or equal to x1. I may not be able to say. But what I know is if x1 is less than or equal to x2 and x2 is less than or equal to x1, then implies x1 equal to x2. And the next one is if x1 is less than or equal to x2 and if x2 is less than or equal to x3, that implies x1 is less than or equal to x3. So, right? So one usually says it's a okay, and of course it's a reflexive, that is x is less than or equal to x for all x. Okay, so it's a reflexive. This is antisymmetric, and this is transitive. Okay, so a partial order is reflexive, antisymmetric, that is if something is less than x1 is less than or equal to x2 as well as x2 is less than or equal to x1, then x1 equal to x2. Okay, and the third thing is transitive. If x1 is less than or equal to x2, x2 is less than or equal to x3, then x1 is less than or equal to x3. The most important example, if you are not sure, please go back to, there is a series of videos on partial order where I have given this Zorn's lemma, okay, with a lot of good examples. If you are not very confident about Zorn's lemma, please search for the video on partial orders in my channel. Okay, and it just takes about 40 minutes or 1 hour. Go through it, you will feel very confident of Zorn's lemma. Anyway, so most important example is, suppose if A is a set, let us say S is a set, and my X is partial power set, that is set of all subsets. Okay, then if I have two elements A and B, that means A and B are subsets of X. I say A is less than or equal to B if and only if A is contained in B. Then you can see this is a partial order. Okay, A is less than or equal to B, that's correct. If A is less than or equal to B and B is less than or equal to A, that means A equal to B. And if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. Okay, this is the most important example. So pause, review, proceed. Please, okay, if necessary, view my video on partial orders. Okay, right? Now let's go back to our original problem. So V is a vector space over a field F, and W is a vector subspace, and F is a linear function from W to F. Right? Now I am going to construct a set capital X, which is set of all pairs of this kind. Okay, let me just write phi, and this is not W. Let us say okay, F1 W1, so that W1 is a vector subspace of B, and W is contained in W1, that is W is less than or equal to W1, and F1 from W1 to F is a linear functional, and when I restrict F1 to W, it must be F. Do you follow that? Okay, think of this as a vector space, and this is my W. Okay, and then the W1 will be some other, this may be my W1, this may be my W1. Okay, and this is my W. Okay, if you want, it may be a good idea to have different colors. This is my W, and this is my W1. Okay, right. All right, so this set X is not empty. Why? Because my FW already lies there. Check that, because W is less than or equal to W, that is W is contained in W, and F is from linear function from W to F, and restricted to W is F. Absolutely no problem, right? Therefore this is non-empty. Is that clear? Now I want to give it a partial order on X. How do I give? Very easy. Let us look at, I have F1 W1 and F2 W2. Remember, what is the most important example of partial order for my containment relation, set theoretic containment, right? Now W1 is a subset of V, of course is a vector subspace, W2 is a vector subspace of V. So what is the natural relation I can have? So I say this is less than or equal to 2 if W1 is contained in W2, which is same as saying that's a vector subspace of W2. And what do I do with F1 and F2? Remember, F1 extends F, right? That is F1 restricted to W is F, and that same as F2 restricted to W. So what do you think I should require now? Remember, I want to keep on extending. So what is the very natural thing I should expect? Since W1 is a vector subspace of W2, if I restrict F2 to W1, I should get F1. And hence, this will automatically imply when restricted to F, F2 is restricted to W, it must be V. Is that clear? Because F1 already extends F. Make sure that you understand this. Okay. And is this a partial order? Yeah, that's very clear, because if I have some W F1 W1, then that's less than or equal to F1 W1. And if you say F1 W1 is less than or equal to F2 W2, and that's less than or equal to F1 W1, what does that mean? That means W1 equal to W2, and hence it follows F1 equal to F2. Okay, make sure that you understand all these things, and transitive is also clear. So make sure that you follow, take some time, do not simply assume. Okay, if these are the small thing, if you verify, you will feel confident how to use Zorn's lemma. Right? So what I have done now? So what I have done now is that on the set X I have given a partial order. So therefore this is a partially ordered set. Right? Now if I want to apply Zorn's lemma, what do I need? Let us recall that if X, this is a partial ordered set, with some property, it has the following property. What is the property you should have? This is the assumption on this partial ordered set. That is, for every subset Y of X which is totally ordered, what does that mean? That means if you give me y1, y2, y and z in capital W, y, then either y is less than or equal to z or z is less than or equal to y. One of them must happen. That is, I should be able to compare any two arbitrary elements of y. One usually calls it a totally ordered set or a chain. Various kinds of words, whichever is familiar to you, accept it. The crucial thing is concept. The concept is, in a partially ordered set, if you give me two arbitrary elements, I may not be able to compare. I may not be able to say x is less than or equal to y or y is less than or equal to x. Like, if I give two subsets of a given set, it is not necessary the set A must be subset of B or the subset B must be a subset of A. I may not be sure. Right? Now I have to be sure. Whereas here it is a totally ordered set. Then any such a totally ordered set has an upper bound. What does that mean? That means there exists an x0 in x such that for all y in y, y is less than or equal to x0. You see this upper bound, because y is less than or equal to x0, therefore x0 is an upper bound for every element of y. Yeah, please understand. So now we want to prove our partial ordered set, which consists of all elements of the form F1 W1 with whatever property has the required property to apply Zorn's lemma. What does that mean? So suppose Y is a collection of Fi Wi such that Fi Wi belong to my X is a totally ordered subset or a chain in X. So what is that I have to prove? I have to prove whether there exists an upper bound. What does that mean? I have to say whether there is some F naught, W naught in X, that is said that for each Fi Wi in Y, Fi Wi is less than or equal to F naught W naught. That means what? Wi must be contained in W naught, and Fi restricted to W naught, sorry, F naught restricted to Wi equal to Fi. Okay, is that clear? So how do I find W naught? Again, that's why you have to look mathematics as a whole. Okay, so recall how you prove R is a commutative ring with identity. It has a maximal ideal. That is, given any I, an ideal in R, there is I naught maximal or J maximal such that I is subset of G. Okay, the trick is, that is why the containment relation is good. This W naught you define to be union of Wi such that Fi Wi belong to my Y. Take all the vector subspaces. Remember, see, you may find that I am trying to confuse you, but one should learn to think. See, this vector subspace Wi may appear with some Fi Wi in Y, as well as some other, let us say Fi dash Wi, the same thing. You understand that? That is Fi dash, both are from Wi to F, but when restricted to my W, it happens to be F. Okay. So, okay, you understand what I mean? Fi Wi and Fi dash Wi, if I take union, it's only Wi. Only these two, right? You understand? Are you following? This is just to learn to think deeply, because many teachers try to avoid. Okay, they make it very streamlined, simple. Okay, it's like leading a horse by its nose. Okay, so you don't see anything else, but you should learn to do this kind of stuff. Okay, now I claim this is a vector subspace. Notice that by definition each Wi is contained in W naught. Okay, so only thing is I have to show it's a vector subspace. That is where we are going to use, it's a totally ordered subset. Why? Suppose I start with the x, y in W naught and scalars, let us say a and b scalars. Then I have to prove ax plus by is in W naught. Right? Now notice that x belongs to W naught. By the definition there is an I so that x belongs to Wi, and similarly there is a j so that y belongs to Wj. Right? Since x belongs to Wi, W is a vector subspace, ax belongs to Wi, and similarly by belong to Wj. Right? But remember, where do Wi, Wj all lie? This is lies in y. That is Fi, Wi, Fj, Wj. They are all elements of y, and these are totally ordered. That means one of them must be less than or equal to other. Therefore, with the loss of generality, let us assume, okay, Wi is contained in Wj and Fj restricted to Wi is Fi. This is where we use the fact it's a totally ordered collection. Right? Therefore, my Ax, By both belong to Wj. But what do I know about Wj? It's a vector subspace. Therefore, Ax plus By belong to Wj. That means Wj is a vector subspace. Okay? Make sure you understand these things. Right? Now the next thing is, how do I define F naught? So if you start with any x in W naught, I know that x has to be in Wi for some I. Okay, there is I such that x belong to Wi. Right? Where Fi Wi belong to my y. Right? Therefore, I define F naught of x equal to Fi of x. Now you can ask the next question. It may also happen x belong to Wj. Right? In that case, I would define as Fj of x. Right? right? Again we use totally ordered. So wi wj, this fi wj and fj wj both are belong to w y, therefore one of them must be less than or equal to the other. So let us assume this is less than or equal to this with our loss of generality. That means, okay, that means what? My x belong to wj and also it belong to wi, right? Now when since x belong to wj and it belong to wi, therefore fj of x must be equal to fi of x, because fj restricted to wi must be fi. Recall our partial order, right? Therefore this is well defined. Do you understand why it's well defined? I want to define f naught of x equal to fi of x if x belong to wi, but that x may belong to some other wj. Okay, it may belong to infinitely many. Then what do? It does not matter. Then in that case I will define fj of x. I want to say fj of x is same as fi of x. That is where we use totally ordered thing. Okay, just make sure you understand. Okay, therefore, okay, my f naught w naught is an upper bound for y. Okay, therefore by Zorn's lemma there exists, okay, a maximal element. Let us call it gz in x. What does that mean? What is, okay? Again, many people have confusion with Zorn's lemma. Maximal element means, see, there are two things. When I say it's maximal, you want to say there is nobody above me. Okay? If you say this fellow is above him, then this fellow equal to this fellow, right? Okay, so in other words, what does it mean? That if you say there exists some h z1, or let us say g1 z1 in x, so that gz is less than or equal to g1 z1, then okay, they are equal. Gz equal to g1 z1. That is, there is nobody above me. Whereas when you say maximum, I want to say everybody is below me. Okay, again, my sincere request, if you are confused about this kind of thing, maximum, maximal, Zorn's lemma, all these things, please go take pains to watch my videos on partial orders. Okay, come back. So there is a maximal element, okay, g z. I claim, okay, z is nothing other than v. Claim. Notice that gz belong to the x, that means g restricted to w must be f, right? Therefore if I prove z equal to v, then I get actually an extension, okay, that is there is a v to f, so that g restricted to w is f. So I got the required extension, right? So I only have to prove this. So make sure you understand this, right? But that's very easy. Suppose my z is not equal to v, that means there exists a u in v, so that u is not in z, because it is a vector subspace, therefore there exists some other element, right? Now let me define a z naught to be z plus f times u. This is a vector subspace. Why? If you have z1 plus a1 au plus z2 plus bu, then it is z1 plus z2 plus a plus b times u, that is z plus fu, right, etc. Right, now I can define a g naught, okay, for any z in z naught, which is of the form, let us say, okay, z1 plus au, z1 in z, and a is a scalar, okay. I will define z1 z naught of z equal to Okay, that is z1 plus a of u to be g of z1. Remember, I want it to be linear plus a times 0. That is g naught of u I want to be 0. Are you following? That is g naught on z is g and g naught of u is 0. So I extend this. Okay, this extension is this. So clearly, okay, g naught is an extension. And remember also my my not g naught, did I use g naught there? G, therefore this is g naught, right? G naught is, so g naught z naught is strictly greater than gz. Why? Because z is strictly contained in z naught as u is not in z naught. Clear? And g naught restricted to z is g, but g restricted to w is f, therefore g naught restricted to w is nothing other than f. Therefore g naught z naught is an element of x, but that is strictly greater than the maximal element. That's a contradiction. Okay, this is a contradiction. So what does this contradiction show? This contradiction shows that my z must be b. So as I claimed earlier, therefore gb is a required extension of f w. Okay, please go through this argument because many of you will have function, and it's typical proof of Hahn-Banach theorem. This kind of thing is very quickly done in less than 5 minutes towards the algebraic part. Okay, so I know many students have difficulty in the algebraic part. Okay, that is why I just went through the thing carefully. Please take your time, go through and watch it. And if you are not very sure about partial ordered z, Zorn's lemma, etc., this is the fourth time I am saying in this lecture. Please watch my lecture videos on partial order. Okay, I hope you enjoyed. In the next session, we will say in the special case where a nonlinear space happens to be a Hilbert space, how easy it is on Hahn-Banach theorem. Remember, now we have to talk about continuity also. Alright, you will see that. For some strange reason, functional analysis books do not even mention that, how easy it is. Okay, we are going to do that. And the last one will be the most coveted version of Hahn-Banach theorem for any nonlinear space. Okay, I hope you enjoyed. We will meet again.